The last part of these notes, we are going to be looking at this thing called electron configuration. If you have taken chemistry in high school before, you probably have talked about electron configuration. If not, no worries. Electron configuration is exactly what it says. It's a description of which orbitals in an atom are occupied by electrons. So it tells you where the electrons are. When we're doing this, we have to abide by a few rules. The first rule is known as the Aufbau principle. It says energy levels in orbitals are filled in order of increasing energy. Here is an example. Okay, now we're fairly familiar, or should be, with our shell. Remember, our shell it's the same thing as our energy level. Okay, so here you have your nucleus. And then you have your first energy level, or your first shell, so that's n equals 1. Right here, this represents your n. Okay, and then you can have your second energy level, n equals 2, and so forth. In the first energy level, with n equals 1, the only subshell that we have is the 1s. In the second shell, we have two orbitals now. We have the 2s as well as the 2p. The third shell, or the third energy level, we have three orbitals. We have the 3s, which is lower. We have the 3p, as well as the 3d. Now this is where it gets a little messy. The fourth energy level, we have four orbitals. We have the 4s, 4p, 4d, and it doesn't show it, but I'll put it in. We also have the 4f. Notice how we get these overlapping orbitals of our energies. When we're doing electron configuration, the electrons are always going to go in from the lowest energy to the highest energy. So we must need to know what energy level is the lowest, which energy is the highest. One way is you can memorize this chart, which is awful. I hate memorizing, right? Okay, the other way is I'm going to show you a cheat way of knowing what orbitals are the lowest, which ones are the higher ones. When we're doing electron configurations, we need to know which energy levels are the lowest, which ones are the highest. Okay, so let's look at for the first energy level. When you are writing this out, you need to be really careful. You have to be very neat when you're doing this part, because you have to have everything line up. In the first energy level, what subshells do we have? We only have the 1s. Okay. Now in the second energy level, n equals 2, what subshells do we have? We have the 2s as well as the 2p. Okay. Next one, we have n equals 3. What subshells are in that one? 3s, 3p, and 3d. Okay, now if I was looking at n equals 4, what subshells do I have in that one? If you can see the pattern, we're going to have 4. We have the 4s, the 4p, the 4d, as well as the 4f. And let's look at the fifth one. How many orbitals are here? There'll be 5. We get the 5s, the 5p, 5d, the 5f. Okay, but what comes after f? Remember, after f, then it's alphabetical, so it's 5g. Okay, now that I have it lined up, now you have to have these columns and these rows. If you don't have them neatly done, then you won't be able to write out the electron configurations. What you do is you draw diagonal lines through this. So we draw our first diagonal line. The first one only hits the 1s. So that's going to be our first orbital. So down here, this will be the lowest energy level. Now I'm going to draw the next line. Draw it diagonally, and it only hits the 2s. So after the 1s, the next highest will be the 2s. After 2s, I draw another line. Where do you think the line will start? Over here, and now it goes through 2 of them. What 2 does it go through? Yep, the 2p and the 3s. The 2p comes first, so I'll write that down, and then the 3s comes second. Okay, and then let's draw another diagonal line. Okay, this is where you have to be really neat. So it's going to go right through the 3p and the 4s. Okay, draw another diagonal line, and we'll see it goes through the 3d, 4p, and 5s. Okay, and then after that line, we'll draw another line. Okay, so it goes through the 4d, the 5p. But if I draw in another line for n equals 6, then it would actually go through the 6s, right? So technically, it's going to also go, or the higher energy level above the 5p will be the 6s. Okay, and maybe just for funsies, I'll draw this last line out. And then we have 6h, which I ran out of room, but it's not going to matter. If I draw a line through this one, we'll continue with the 4f, the 5d, 6p, and then notice how we have that 7s down there. Okay, so the whole reason we're doing this is to show what energy levels are the lowest, which ones are the higher ones. This allows you to not have to memorize that previous figure. So the 7s, or the ones that are higher, are going to have the higher energy levels. Okay, now what I also need to do is I need to put in how many electrons each orbital can hold. For the s orbital, how many electrons can be found there? The s orbital can only have one, or can only, let me rewrite this. The s orbital will only have one orbital. So we draw a line like that. And remember, each orbital can hold 2 electrons. So the s can hold 2 electrons, one up, one down. Okay, so the s can always hold 2 electrons. So 1s, 2, and then now the next one we have a 2s. Again, an s orbital will only hold 2 electrons. Now let's look at the p orbital. How many orbitals can the p have? The p can have 3 orbitals, right? Because you can have the px, the py, and the pz. Now each orbital, so I should write 3 orbitals. And each orbital can hold a total of 2 electrons. And each orbital will have one up, one down. So this one can hold a total of 6 electrons. So wherever you see a p, you can write in 6 electrons. Okay, and then wherever you see an S, you can put in 2. So 3s2. Now we are coming to the next one, which is the d orbital. How many orbitals are in the d? There are a total of 5. And so so 5 orbitals, and each orbital can hold 2 electrons, right? So that gives me a total of 10 electrons. So every d orbital can hold up to 10 electrons. So wherever I see a d, I'm going to put 10. The last one we will look at is the f orbital. The f orbital will have how many orbitals? There will be 7 of them. And because each orbital can have 2, there's going to be 14 electrons. I'm not going to draw them all in because I'm lazy. But wherever I see an F, I can put 14 in there. This, what we drew down here, this is known as the electron configuration. Each atom will have a different electron configuration because each atom will have different numbers of electrons. What we did here is just showing you where the lower energy levels are, where the higher ones are, and also how many electrons can be in each orbital. When we're doing electron configuration, another rule is each orbital can only have 2 electrons and they must be of opposite spin. We've already kind of talked about this. You can have a spin up, so you have a half arrow going in the up direction, and you can have a spin down, so an arrow going down. The second rule is the Pauli exclusion principle. It says no 2 electrons can have the same quantum numbers. There can only be 2 electrons in each orbital. Again, we've talked about that. And another rule, you have the Hund's rule. Every orbital in a subshell is filled by a single electron before any orbital is doubly occupied. All electrons in single occupied orbitals spin in the same direction. Okay, for example, let's say you have a p orbital. A p orbital, or I should say a p subshell, has how many orbitals? It has a total of 3 orbitals. So these lines represent orbitals. Now let's say you only have 3 electrons in there, but we know that they can hold up to 6 electrons. So the up to, that's the key. Sometimes they'll only hold 3, which is fine. If they only hold 3, it says that all electrons in a single occupied orbital spin in the same direction. So one will go up, the other one will go up. So they all spin in the same direction. You cannot have this. You can't have one spin up and the other 2 spin down. They have to be all in the same direction. Okay, and then the other part that it's talking about is, I'll draw it here. So let's say you have your p orbital, but let's say we have 4 electrons in there. So you fill each orbital first. So one electron in the first, second, third. The reason why is because electrons, they don't like to be next to each other. So they're going to fill the other orbitals first. Okay, so now we have 3. Everything is half filled. So now we can doubly occupy one of them. It doesn't matter which one we occupy. So it will look something like that. Now let's actually do a problem involving electron configuration. It says write the electron configuration of boron. The first thing we need to do is find the number of electrons. For a neutral atom, if we remember, the number of protons will equal the number of electrons. If you looked at boron, how many protons are there? There are a total of 5 protons. So that must mean that there are going to be a total of 5 electrons. The second thing is place the electrons in the lowest orbitals until you reach the total number of electrons. This is known as the orbital filling diagram. Okay, what you need to do is refer back to when we drew out that very long electron configuration, and so you start from the beginning. The beginning electron, or the beginning subshell, was the 1s, and the 1s has only one orbital, so I only draw one line. How many electrons will go in there? 2. So one will go up, one will go down. Okay, so far I have only used 2 electrons, but I need to get 5, so I need to go to the next subshell. What is the next subshell? According to my drawing, the next one was the 2s. The 2s, how many orbitals does it have? The s orbital only has 1, so I draw one line. How many electrons will go in there? 2, because remember each orbital can only have 2 electrons in it for a maximum. Okay, so far I've used up a total of 4 electrons. I need to get 5 electrons. So after the 2s, what comes after that one? The 2p. How many orbitals does the p subshell have? It has a total of 3, so I draw 3 lines. How many electrons should I put in there? Okay, that you might get confused right here. The p orbital can hold a total of, or it can hold up to 6 electrons. Even if it can hold up to 6 electrons, you don't need to add 6 electrons because you need to get a total of 5 electrons in our electron configuration. So far I've used up 4. That means I have to only put 1 in the 2p. I'll put it in the up direction. Doesn't matter though. It could have been in the down direction. So this is known as the orbital filling diagram because you're filling the orbitals. Now let's write the electron configuration. The electron configuration will be, it'll look something like this. You have the 1s and you have 2 electrons in there, so 1s, 2. For the second one, you have the 2s and you have 2 electrons in there. And then the next one you have the 2p, and how many electrons are in that one? 1. So this is your electron configuration. Here we have a problem, and it says write both the orbital filling diagram and electron configurations for the following. Let's do carbon together, and then you can do nitrogen on your own. So for carbon, we need to do the orbital filling diagram first. Okay, so the orbital filling diagram, I start with the lowest one. Oh, before I do that, I should first figure out how many electrons carbon has. How many electrons does it have? It has a total of 6 electrons. Alright, so now I can start my orbital filling diagram. The first energy subshell is the 1s. The 1s has one orbital, and I'll put in 2 electrons there. So far I've used up 2. The next orbital is the 2s. The 2s has one orbital as well, and because each orbital can hold 2 electrons, I'll put 2 in there. So far I've used 4. And then the next orbital after 2s is going to be the 2p. Because a p orbital, or I should say a p subshell, has 3 orbitals, I'll draw 3 lines. How many electrons should I put in here? Well, I need to get 6, and so far I have 4, so I'm going to put 2 in there. So they're going to be in separate orbitals. So it'll look like something like that. Could you have this? No, you can't have this because the electrons want to be in their individual orbitals until they can't anymore and they have to pair up. So this will not happen. Okay, and then now let's write the electron configuration. So we start with our first orbital, 1s, and we have 2 electrons in there. Then we have the 2s and 2 electrons in there. And then the 2p with 2 electrons as well. So as a reminder, this number that's superscript, that's the number of electrons. The 1, or the number out here, the coefficient, this is your shell. This is your n quantum number. And then your, for example, the s here, this is your subshell. Your subshell is what your L, your quantum number L, is representing. Okay, I want you to do n by yourself. Again, you're going to do the same thing. You're going to write the orbital filling diagram and the electron configurations for oxygen, fluorine, and neon. And we'll check your work when you get to class.